In this lecture, we're going to talk about the T-triangle. The T-triangle will be useful for us to try to understand these T numbers. It's just going to be something like Pascal's triangle, but the entries of the triangle will be the T numbers, and I'll show you what we mean. We're going to start with what we call row 1, where we'll put T11, which is just 1. Row 2, we'll have T21, which is just 1. Remember, TM1, I'll put this note over here, TM1 is always going to be 1. This is for any M. And remember, on the right side here, T22 will be 2. TMM will be exactly M factorial. So T22 will be 2 factorial, which is just 2. So this is T22. This is going to be T21. This one here was T11. The next row will be T31, T32, and T33. T31 is just 1. I won't write that's T31, but that's what we mean. T32 we can find using the formula above. Remember, put these formulas back here. TM2 will be 2 to the m minus 2. So that will be 6. 2 cubed minus 2 is 8 minus 2, or 6. T33 is just 3 factorial, which is 6. And I'll stop writing the row numbers. Row 4 will have 4 elements. T41, T42, T43, and T44. Notice that the numbering is for our row numbers and even our position numbers is slightly different from Pascal's triangle, when we always started with 0. For the T triangle, we're starting with row 1 on top, and each row will be indexed starting from 1 and going up to the row number. So T41 is 1. T42 is just 2 to the 4th minus 2, which is 14. T43, we could actually use this formula for TM m minus 1, which I wrote down above. That's m choose 2 times m minus 1 factorial. So T43 will be 4 choose 2, or 6, times 3 factorial, which is 6. So we have 36. T44 will be 4 factorial, or 24. So I'll just put in these. Let's look at row 5. I'll put in the row numbers just so this stays clear. Row 4 here. Let's look at row 5. T51 is 1. All the rows will start with 1 because of this. TM1 is always 1. T52 is 2 to the 5th minus 2, so we're going to get 30. T53 we computed in the last lecture, that was 150. T54 we can compute from this, TMM minus 1. So what is T54? It's 5 choose 2, which is 10, times 4 factorial, which is 24, so we get 240. And T55 is 120. Now, you can compute the entries for row 6 pretty easily. I'll just write them down here. They're going to be, sorry, let me check those. In fact, I'm not even going to write down row 6. I'll leave you guys to write down row 6 on your own. Try to finish it. Try to write down row 6 and row 7. These are good exercises and will help you in computing these. Remember, you can always go back to the definition of the T numbers, which said that TMN is just going to be a sum of these distribution numbers, M, M1, M2 through Mn, and it's a sum over all the types of distributions where M1, M2 through M sub n are each at least 1, and their sum is exactly the total M. So using that, you can fill out other rows. Now, why are we putting these T numbers and arranging them in a triangle? Well, the triangle will help us see some patterns. And you can see the patterns that are given by these formulas in these diagonals on the left, the second diagonal for this formula here, the diagonal going the other way on the right comes from this formula, TMM is m factorial. The second diagonal from the right is here, that comes from this formula here. But do we see some other sort of relationships? And we might ask, is the rule something like Pascal's triangle for creating entries? Is this entry the sum of the two numbers above it? Well, you can see 6 is not 1 plus 2, but you might notice it's double that. Well, that's interesting. Maybe that happens other places. Look at this 14. Is that 1 plus 6? No, it's double that. The 30, is it 1 plus 14? No, it's double that. Is that a coincidence, or is that some important pattern? Maybe each entry is double the sum above it. Well, look at this 36. 6 plus 6 is 12. That 36 is not twice 12, but it's actually 3 times the 12. This 50, above it you have 14 and 36, which add to 50. 150 is 3 times that sum, 50. So somehow the 150 is 3 times the sum above it. The 36 is 3 times the sum above it, even though each of these entries was just double the sum above it. Let's look at 240. Well, above it you have a 24 and a 36, which add to 60. 240 is 4 times that 60. So something kind of interesting is going on. The 30 is twice the sum of the two numbers above it. The 150 is 3 times the sum of the two numbers above it. The 240 is 4 times the sum of the two numbers above it. Interesting enough, we could also extend that this 120 is actually 5 times the sum of the numbers above it, the 24 there, and think of a 0 off to the right, because you can't go any further. It should be very clear that TM m plus 1, or anything bigger than m plus 1 here, would have to be 0. You can't have a distribution of m balls into m plus 1 boxes and have no empty boxes. That wouldn't make any sense. So think of zeros everywhere off the triangle, and you get this pattern kind of extending. Well, how would we describe that pattern? If we want to look at TMN, it seems like it's related to the two things above it. The two things above it, above left, will have Tm minus 1, n minus 1, and above to the right will have Tm minus 1, n. And if I add those together and multiply by the appropriate thing, maybe I will get TMN. And what does the appropriate thing look like? Well, things in the second position seem to be double the sum of the two numbers above them. 30 is double this, 14 is double that, etc. The things in the third position look like they're triple the sums above it. Things in the fourth position, we only have one example, or you can use 24 as 4 times 6 plus 0 if you want as well, are 4 times the sum above it. And in the fifth position, maybe 5. So we have to ask, what is the position here? And the position is the n. So we're going to put an n times Tm minus 1, n minus 1 plus Tm minus 1 comma n. And we ask the question, does that always hold? Well, here's that same recursive formula that I just wrote down. Tmn is n times Tm minus 1, n minus 1 plus Tm minus 1 n. And I claim now this is true for every number n between 1 and m. Let me show you a quick example of this, and then we'll talk about why this is true. Well, we've already computed T53. Remember earlier we asked how many distributions are there of 5 distinct balls into 3 distinct boxes with no box empty. We found there were 150. We put that in the triangle above, and that's the number T53. But let's say we use this recursive formula and nothing but that recursive formula. Well, that would tell us we just take the n, which is 3, times Tm minus 1, n minus 1 would be 4, 2, plus T4, 3. Now the question is, what is T4, 2 and what is T4, 3? Well, this is a recursive formula. We get T5, 3 in terms of smaller t numbers, so we can just compute those separately and put those numbers in. T42 is going to be, by the same recursive formula, 2 times T31 plus T32. Now T31 is always going to be 1. Anything with a 1 here is the second entry. We'll get 1. What is T32? T32 we can write as 2 times T21 plus T22. And similarly, remember, we're going to stop when we get to TMM, which is just m factorial. So this will be 2, and this will be 1. T32 is 2 times 1 plus 2, which is 6. We put the 6 here. T42 is 2 times 1 plus 6. That's 2 times 7, or 14. And now let's ask about T43. T43 is, by the recursive formula, 3 times T32 plus T33. And remember, T32 we just computed, that's 6. T33 is going to be 3 factorial, which is also 6. So T43 is 18. So we can put in 18 for T43. And what did we compute? 14 for T42. That's not correct. What did we do wrong here? T42 was 14. T43 is 3 times 6 plus 6. It's not 18. That's 3 times 12. That's 36. Let's get this right here. 36. 36 plus 14 is 50 times 3 gives us 120. Not 120. That's 50 times 3. That gives us 150. I can't add or multiply today, but there we have it. The correct number is 150. So the question is, it's not a question here. We can use this recursive formula essentially to compute the t numbers row by row, as we might do with Pascal's triangle. Or if we start with T53, we can just work downwards until we get to points where we already know the answers. If you have a computer, you can program it with a very simple program to compute TMN for any given value of m and n, and it will just run recursively until it finds the answer. It's a very easy thing to write a program for. But before we just accept that recursive formula, let's ask, is there a way we know this recursive formula is true? How do we know that this always holds? Looks like it holds just at the beginning of the T-triangle, but that's not good enough. So I'm just going to get myself a little extra space and ask, why is this true? Why is TMN always equal to n times Tm minus 1, n minus 1, plus Tm minus 1, n? And this will come from, we'll give a combinatorial reason for this. We ask, what does TMN count? This counts the number of words of length m from an n-letter alphabet where we use all of the letters at least once. Well, let's say I want to construct such a thing. Here's an m-letter word. How many ways could I pick the first letter? Well, there are n letters. I'll just put x here. I have m ways, not m, I just said it before, n ways. Kill this. I'll say it again here. N ways to pick the first letter. Now, once I pick the first letter, how many ways can I finish? M letters total. To finish, I have to pick this word with m minus 1 letters. And it might seem like it's hard to answer, how many ways could I finish this word? But I'm going to divide it into two cases. Case 1. We don't use this same letter ever again. And I'll write no more x's. That means we never use that x again. Well, if we never use that x again, this m-1 letter word comes from an n-1 letter alphabet because there are no x's. And we need each of those n-1 letters to be used at least once, because then in our original word we'll have all n letters used at least once because x is used for that first letter. And how many ways can I choose an m-1 letter word using all letters from an n-1 letter alphabet? Well, there are t, m-1, n-1 ways to do that. Case 2 is I use another x. Maybe more than one x, but there's at least one more x in here. Well, if there's at least one more x in here, since the whole word has to contain one of each letter, this finishing part, the last m-1 letters, contains an x, and it has to contain at least one of all the other letters as well. In other words, it has to contain at least one of all n letters. And it's a word of length m-1. How many ways can I do that? Just t m-1 comma n. That's the number of ways I can pick an m-1 letter word using every letter from an n letter alphabet at least once. What's the total number of ways I can finish? I'll write it up here. This is the number of ways to finish the word. So we have n choices for the first letter of the word, and this many choices, tm-1, n-1, plus tm-1, n, ways to finish the word. That gives us our recursive formula for tmn. And using that recursive formula, you'll find you can easily compute row after row after row of the T triangle and finish as many rows as you want.